So this time I'm really going to talk about similarity solutions to PDEs. We've kind of, every single solution that you've looked at so far has been a similarity solution. And the group of, well, I'm leading you into the group. It actually forms a group if you look at all possible similarity solutions to a PDE. So I'm going to start with the heat equation. And the idea is that you wish to find, instead of how do you come up with these invariant solutions? I mean, really, the way that we've looked at it historically is that people just seem to kind of come up with something, they tried something, they believed something, and they just tested it out. But really, you could systematically go about finding a similarity solution by saying that you want to find solutions that are invariant under certain kinds of transformation. Let's say, for example, I wanted to be invariant under scaling transformations. So here I'm allowing a scaling in x of this type, a scaling in s and t of this type, and a scaling of this should be a u here. There should be a u right here. So then you have a scaling that's also of the original solution. And then you can pop those transformations. So invariance means that you want to plug this into the formula, into the equation, and you want things to remain the same. You still want this scaling solution to be a solution. So that means not all choices of A, B, and C will work. Only some choices of A, B, and C will work. So you drop these guys in, and I just copied and pasted even my erroneous solution, so that should be a U in there. Not U should be here, but U.
Why did you put U in and move it down?
I don't know if it might fit, yeah. Let's try it. Yeah, it does fit there. So what we're doing group theory, because you know how much I love algebra. Yeah, and I'm teaching it next semester again, so.
I must have thought you did a good job, because Lee's teaching discrete.
Yeah. Or next semester?
Yeah.
I'm teaching this class by accident too, so. So just to back up, you have this original heat equation, and we've gone through the history of why people made decisions like, oh, I'm going to look for solutions of this type. But how do you systematically find all the solutions that are invariant, right? That's the whole trick, is you want to find something that you can plug in and make some assumptions about what the solution will look like. And so far it seemed like people just stumbled on them by accident. D'Alembert just made a guess, and Laplace just made a guess. But how do you systematically do that? Well, you can look for all possible solutions of, let's say, scaling transformations by taking x and scaling it, t and scaling it, and u and scaling it. So there should be there is a u right there, right? So somewhere it got lost. But you want to scale by every one of the letters and then plug it in, and not all choices of A, B, and C will work, but some choices will. And you want to hit upon which choices work, because it'll give you the full, I'm leading you in, it's a group, the full group of transformations that will remain invariant. So you drop this back in. And of course, you recall when we did singletons that we actually had to solve for x, t, and u so that we could take derivatives and use the chain rule. So it's probably a useful idea to have the red formulas ready when we drop them in. And so we can do the same things we did with all the different kinds of solutions we've done in the past. We take the derivative, we pop it in there, we get the chain rule, s prime of t is equal to epsilon to the b, and pop them into the equations. It gets a little messy. So ut is epsilon to the b minus c vs. And then ux is epsilon to the minus c vz times z prime. Z prime I've already calculated is epsilon to the a. Ux is epsilon to the a minus c vz. Drop it all into the heat equation. If you noticed, instead of z prime, I've dropped in epsilon to the a. And I'm going to get two of them because I had one derivative and then another derivative. So you get finally this equation right here. And so if you want invariance, then you want this side and that side to be equal because it left it untouched when you popped it in there. So that will happen if these exponents are equal to each other, then you can cancel them from both sides and they're gone. And so you now have a relationship between the A's, B's, and C's that will make it. So this is how you find the full group of these transformations. I will prove for you at the end that it is indeed a group. A group just like we had from algebra class. It's a group of transformations. And for your flip, shift, your game, you can think of it as actions. You're actually moving things, you're rotating things around. So you are actually transforming and moving things. So it's a group action. What that means is if u of xt is a solution, then so is v of zs when v is equal to 2a. So this is kind of the backstory to what I showed you last week, where you have the solution as the error function. Like, where did that come? It's almost like, oh, I'm just gonna, let's see what I have in my hat today, and this is the formula I have in my hat today. And it might be indeed that they found it that way. They just were playing around and messing around and noticed some relationships and plugged it in and got lucky. So now the idea is to solve it, of course, for this entire group of solutions. So first, notice a few relationships, and this should be reminiscent of some of the calculations we've already done. We're going to solve for v in terms of u in a certain way, and we're going to use the fact that s and v both have this relationship. And if you recall, last time when we were doing the specific case where we ended up with the error function, there was a lot of like, I'm going to plug this in here and plug that in here and make it work. So we're doing that in general now for this general transformation. So what that does here is these two things cancel, and this gets messy. So I'm looking for solution. What happens is, so we have this guy down here, and I want it to remain variant. So that kind of tells me that I'm seeking solutions of this type, because this will be my g of nu, and this will be my scaling, and my nu will be of this type over here, x divided by t to the 1/2. Where did 1/2 come from? Well, the relationship between a and b scales to 1/2, because a is 2, right? A is twice b, so they cancel and get 1/2. So that's how they came up with the 1/2. I mean, I'm not pretty sure they didn't do it like this. I think they messed around and guessed. So what about the c over v? So these are where the nice constants come from if you want the backstory and the theory. And that was applied to the heat equation. So I'm not going to go further than that. I did that last time, where you plug this in and you do a lot of work and a lot of calculations, and you end up with the error function at the end, right? But we can try this approach on more complicated problems. It doesn't have to be something as simple as the heat equation. So here's a more complicated problem as an example. You have ut and you have a ux with an x, another x partial in it, and I'm sure it means something. And you can assume that the initial condition is what we call the Dirac delta function. The Dirac delta function is it's not really a function. It shouldn't be called a function. It's an impulse. So you get a blip right at 0. So as u of xt, this is a sloppy definition, but u of xt goes to 0 as x goes to infinity and minus infinity. But right at 0, you have a spike that goes to plus infinity. So it's not a function, right? It fails what the kids call the vertical line test. And you also have the property that the integral of this entire u of xt dx is equal to 1. And these kind of things usually come from probability, right? The sum of all your probabilities are equal to 1. That's why I think it might be nice to have a probability class. So this is the informal definition of the delta function. We don't really write that, but I wrote it just so you can think of it this way, that you have a spike going to infinity right at x equals 0, and it's 0 everywhere else. And that the integral from minus infinity to infinity of delta x of dx is equal to 1. So there's my transformation, and I can pop it in there, and I'm going to get a mess. So hold on to your seats. The ut and the uxx still come out from the previous calculation. And I can actually expand this guy with the UX, with the X inside, expand it, dump it all in, and I get this mess. Right? You just have to believe me, because I made several mistakes doing this, and I got to erase them and go back and fix them. So you just have to believe me right now. Lots of calculations. So if I do that, I get this mess right over here. And this mess over here turns out to be the 1/2 epsilon to the minus 2c v squared with a double derivative in z. You know, when people do these calculations all the time, they start to see these, that this is a backward product rule of this thing. I used to be in this area, and after a while you just get used to looking at it and go, oh, that's the derivative of 1/2 v squared twice. You just see it because you have done so many of the calculations. But I put in the little work in there so you can see why that's true. I'm cracking open actually some books from the past and looking at it again. Back then I didn't have algebra, so I was not looking at this the same way. To me it was just a substitution and I'm plugging and chugging. But now I have that algebra background and looking at it and going, wow, this is actually really, really cool. Okay, so this is now, all I've done is I've substituted in this fact right over here. Now I'm looking for invariance, like I did with the heat equation. So I can cancel out that epsilon to the b minus c if b minus c is equal to 2a minus 2c, or I can break it down to a relationship more complicated than the one I got from the heat equation, that c is equal to 2a minus b. This kind of suggests that we're looking for solutions of this type. And we need to translate those boundary conditions. So if we translate those boundary conditions, it was that 1 is equal to the integral over the boundary, which is minus infinity to infinity, u of x t dx. And if I plug in this substitution in here, so I don't have a formal thing lock on what these kind of numbers will look like yet. Hopefully that I apply more of the boundary conditions, I'll get rid of them. Make a change of variables. Right, you would think to do that because the inside of the G, it has some mess in there. So make a change of variables. This is just U substitution, W substitution in this case. And once I make that W substitution, I get this integral. But I know that this integral has to be 1. And the only way that can happen, the only way this integral can be a constant for all values of t is if this exponent was equal to 0. So it wipes out. When you set that exponent equal to 0, you finally get some relationship between your a's and your b's. So we have to work a bit harder than we did with the heat equation to get the relationship between a's and b's. So there's always going to be some kind of constraint on the a's and b's to force the invariant solutions. So we get 3a's b, or 2a minus b is equal to 2b over 3 minus b, which is minus 1/3 b. Why did I do that? Because if you recall, I had this form of the solution that I'm guessing at now from the invariance that I had plugged in. So I wanted somehow to come up with a number for this. And that's why I did that calculation on top to get the minus 1/3. So that tells you that a over b is 1/3. And I get this as my suggested toss this in and let's see if it works solution. I moved from this kind of math to pure math, and I remember just having notebooks and notebooks of computations with lots of mistakes in them. But it's a lot of computing. So there's my u. We put it back to the differential equation. Now it's just what we did in the last few times. You just throw that solution into the equation, and then you get an ODE out of it, and from the ODE you extract the solution. So stare at that for a while. It's this is about 8 hours of notes, by the way. I'm blasting right through it. It's interesting to take this and put a story to it. Like you're just computing these things out, and you're like, wow, now I see this whole thread coming through. And eta in this case is x times t to the minus 1/3. So you can solve, just like we did before, we have to not only have the relationship with eta, you also want to go back and forth with t. So to plug in the rest of this, we need that transformation and the equation. Messy, messy, messy. So what's happening here? I have the UT, it's a big mess, but I still need all that other stuff. Remember that long equation I had at the very beginning? I have to take this transformation, put it in that long equation that I had at the beginning. So I drop it in, plug it all in, I get this particular mess down here, which turns out to be the red equation down below. After some mistake making, erasing, and recalculation, you arrive, maybe I'm the only one, but you'll arrive down at the red formula down at the bottom. It's messy. Some people like to compute, but I found this particularly unpleasant. So when I did this calculation, I got something different than, this was a paper by Oliver, I think. So I got something different than they got right there. They got that 2g prime of n. I got a g prime of n squared, and not n, eta, but I calculated this several times. I still get a g prime of eta, and I don't really see how you're not going to get a g prime of eta squared in there, because when you take the derivative twice, you're going to get g prime and g prime again, and you have to multiply them. You have an ux times ux in this problem, so how would you not get the square in there? So I'm pretty sure they made a mistake. So you can do the, huh?
Are you going to write them about it?
It's pretty old. I think they're not alive anymore. I don't think they're alive.
There's some really good forwarding services out there.
I'll go drop something in at church. But I'm going with their wrong answer. Like I said, you can do the calculation too. I got a g prime square of eta squared. And see if you get something different. I don't see that it goes away. I don't see a 2g prime showing up anywhere. So I'm pretty sure they made a mistake. But if you go with their wrong answer, you have the same deal. You get an ordinary differential equation that you have to solve. And it's not as pretty an ordinary differential equations as we've had so far. It's messier looking. It turns out this is reverse product rule. Again, you get to recognize this the more you compute these things. And my memory is coming back. You've done these a long time ago. You do that again. You feel, oh yeah, I remember doing this all the time. So that piece right there is really eta g prime. This piece right here is gg prime prime. So it's a backwards product rule of this thing. So that's, now you've got two derivatives. So now you can integrate. Integrate straight across. So if you integrate straight across, you get that 3 times gg prime plus eta g is equal to a constant. Now they just went ahead and imposed a condition, an initial condition, which, you know, again, I felt like they were a little sloppy and didn't explain what they were doing, but that gives you that the C1 is 0. And so you get this guy, which now you can cancel the g's out of both sides and actually solve. So they wrote the C1 in a certain form so they could get a nice looking solution for this. If you go and put in the boundary conditions on this thing, you get g of eta is equal to 1/6 a squared minus eta squared if eta squared is less than a squared, and 0 otherwise. Now recall also the imposition of the integral condition that you had. If you plug that in, you get a formula for a. A has to be the cube root of 6. And I think they had a mistake here too. I did the calculation several times and I get A has to be cube root of 6. I'm perfectly capable of making a mistake, but I'm pretty sure that this is okay. So you get this u of xt. I mean, of course, I could have gone back and checked that this was actually the solution, but I'm still pretty convinced that there was an error a little bit earlier. Yours is easier. Do the same thing for ut plus ux is equal to 0. And just to help you along, because the computations are messy, a hint is to let a over b minus 1 be a constant. Call it m. And the DE that you should get after you do all the calculations is g prime minus beta g prime is equal to 0, which you're going to be able to solve for. You should get, I think you get something like u is equal to x over t. So it should scale out pretty nicely.